So now we're going to look at something called photon mapping. So we're going to look at some techniques that we cannot get so far with our ray tracer. So this thing is called a caustic. And so where does this come from? So I think you can just use your physics reasoning. So somebody tell us, where is this thing coming from in physics if this was the real world? How is that light getting there? Somebody tell us what you think. Like, I don't know, I have light over everything, but somehow I got a bright spot. Why is there a bright spot here?
It's sort of it's getting I'm not sure. I guess sort of you could say concentrated by like it's reflecting off of the metal, but getting reflected in a concentrated way.
Yeah, that's the right way, right? So the light comes in, it hits this metal. This metal is acting as a focusing agent. So you can think of it as a lens of sorts, right? And it's focusing this light here, right? If you've ever taken a magnifying glass out and shined it, maybe this picture's closer, right? This is a caustic also. This glass is acting as a magnifying glass. So rays of light are coming in, and lots of the light that passes through lands in the same place on the other side. So now this, our explanation that we just gave said the light comes from our light source, hits this thing, and then somehow it all gets focused. But that's not our calculation so far. Our calculation so far says we start from the eye and we send out light, right? So we get to this point on the table. Let's take one not in the light first. We hit this point on the table, we look up the texture and we say, oh, this is a diffuse object. Forget it. I don't need to send any more rays. All right. And then, so we just know it's in light or not. Well, we get to this point on the table, it's still a diffuse object. The table's diffuse, so we don't send any rays. So how do we know anything about that light focusing? We don't know it yet in our ray tracing algorithm. So then maybe we're going to say like, okay, I'm going to have to send a lot of rays. So I'm just going to send rays in all directions and find out, did I hit the light eventually or not? Turns out that's a lot of rays, because this bright spot is coming from, one ray hit here and one ray hit here, and they somehow all magically focus back onto the light source. It turns out that that's a very noise-prone calculation to do this in reverse. And it would be the same here. So what are we going to do? We're going to go in both directions at once. And so this is called photon mapping. So we're going to start first from the light, and we're going to send out photons from the light, and we're going to let them reflect off of objects and or stick to objects. So you can think of these as being sticky photons. And we're going to, when they reflect off an object, they may land in a new place. And if I have a curved object like I had before, a lot of them may land in the same places. And we're going to store all these photons on the surface. And we're going to do that as a first pass. And now we have stored on all of our surfaces some kind of photon map or light map that says how much light got to this point. And we might have to trace down our tree of waves, right? There could be reflective objects. Or in the case of this transmissive, right? I had to come through a surface, maybe go through the liquid, come out another surface, right? There could be complex interactions happening, but finally the photons are sticking down here. And then we're going to come back and do our ray tracing pass. So we're going to go in both directions. And now when we come back to our ray tracing pass, when we pick up a color, instead of only saying we're going to send a ray back to the light to check it, we're also going to check, hey, are there any photons stored nearby? And if there are, let's add in some light for that. And so those added in photons can contribute to the light. So now we can get to this, because there's going to be a bunch of photons stuck on the table here from pass 1 that we can use to calculate lighting efficiently in our pass 2. The problem's coming because light can bounce around in all kinds of crazy ways. And so now we had to go from both directions to try to get efficient. So this is photon mapping. So here's a picture of an even more complicated scene from some research paper that basically said, like, look, I have this water which is making caustics on the bottom of the pool, and there's some very complicated pathways happening here. And if I try to do path tracing, which is a generalization of the photon mapping, and I use 210 samples at each pixel, I still get this noisy thing, right? It's just too complicated. I can't get a good estimate of what's happening. So what is this Metropolis light transport they're talking about? It's a numerical method. Like if you've taken a numerical analysis class, you can think of when we send a bunch of rays and add things up, we're trying to approximate an integral. And so now we tie to your numerical analysis classes. We could approximate an integral by taking a bunch of evenly spaced samples, but there's other ways we could try to approximate that integral. A bunch of fancy math tricks. And this is saying if we play those fancy math tricks and pick the right samples, we can get away with even fewer samples and get a nicer picture. So I haven't really told you how this works, but I just wanted to give the hint that in a ray tracer, it's very easy to get noisy pictures like this because you didn't send enough rays. And sending more rays, I might have to send a lot so that it gets too slow. So this is always the trade-off in a ray tracer, is getting these kind of noisy pictures if I want to get all the effects, and taking too long. This comes up a lot. Now, in our triangle-based graphics, we couldn't even get this at all. Forget it. We have no idea how to calculate this. If we want water that looks like this, we're going to put some texture on the bottom of the pool and call it good. Right? That's what we can have. Maybe stick a little sine wave, wavy thing in our fragment shader to look up different parts of the texture and say, like, I don't know, close enough. It looks like water. With the ray tracing, we're actually calculating something that's reasonably close to physically relevant. Okay. The last thing I'm going to talk about is real-time ray tracing. But let me see if there's any questions so far up to where we're at. I see a comment in the chat that, like, maybe I wish I knew the physics a lot better. So actually, I think we don't actually require you to take physics as part of your CS degree right now. There's a lot of debate around that. I think that may be coming back. We've been having faculty debates about whether we should or should not require physics. And it was taken out not because, thanks for the clarification. I think that's the correct current state. So the reason that it's not required in CS, it used to be required. And the reason it's taken out is not because we decided it wasn't good for you. It's taken out because the physics department said, my God, there's too many computer science majors. Like, could you please stop? And so as a service to the CS department, to the physics department, we took it out of the requirements. However, there's a bunch of places in computer science where it comes up to be useful to know at least something about physics. So there's a current discussion going on. So I guess in another 2 years, the new students are going to be required to do physics again. Well, the world changes. I think they decided they want the students now. There's a bunch of complicated accounting on campus, right? If you have too many students, it's hard to teach your classes. If you have too few students, then your budget starts to go down. So I think they now want you back, but they may not understand how many of you there are. So anyway, lots of computer science professors wish there was physics. In graphics, it comes up in some places, as you've seen over this course, especially in a lot of the stuff we talked about today in the ray tracing. The place it really comes up is in your architecture classes and other places. Knowing something about how the hardware in a computer works, physics comes up. Anyway, this is a divergence. How did I get diverted? That's the professor, I don't know what it's called, the nemesis of professors, easily diverted onto wrong topics. Okay, real-time ray tracing. So you see this, I have no idea how this works. I never used any real-time ray tracing. This is a pretty new addition, so I've never actually written code for real-time ray tracing on any of these modern graphics cards because it's a relatively new thing getting added. So I just haven't dealt with it. So I'm going to say only some high-level things so you know something about what's going on, right? So you see NVIDIA is advertising that their real-time ray tracing is here, right? And if you wanted to pay us a lot of money, you could have it. So that's what companies do, right? Okay, no surprise. They have something like this. What does that mean? So if we go look at what's actually in a graphics card, it's going to be a parallel processor, and there's going to be a bunch of individual units for doing vertex shading computations. They tend to be highly optimized for doing things like matrix times vector, right? The kinds of stuff you were doing. And there's going to be, it may be combined together, it may be separate. There's going to be some other cores which are there for calculating fragment shaders and the kinds of calculations that you need there, because we do a lot more fragment shading than we do vertex shading in a typical graphics render. So there may be different numbers of these multiprocessors. Now machine learning is there, so you start to see things talking about, you know, tensors and these kinds of things on the chips for helping machine learning and the kinds of computations, the convolutions and things that happen there. So now they've added some cores somewhere in here. They've added some specific hardware to try to deal with tracing these rays in an efficient way, right? So this is what they mean when they say they've added it. They've added some specific hardware to go try to make the ray tracing fast. I want to mention that the idea is not new, right? So here's SIGGRAPH, the main graphics conference, 2005. I took this slide from a course called Introduction to Real-Time Ray Tracing. So people were talking about real-time ray tracing in 2005, and there was enough known that they were teaching courses about how would this work. So what's changed? So one, 15 years is about the right amount of time. 15 to 20 years is the typical time from, you know, academics talking research to you can go buy a product. That's usually about the time frame we see for things to make it from idea to somebody commercialized. The second thing is we were doing this at that time, the real-time ray tracers, and even before this, I should say that there were specialized hardware to do real-time ray tracing, but they were specialized and not widely available. NVIDIA is widely available, and I don't want to pay $2,000 for my graphics card, but that's basically cheap if you compare to custom specialized hardware that might be $50,000 or something. So it was there, but it was more like you have to write some very custom code. So now it's much easier to use, and it's packaged up into something that you can get, right? It's expensive, but you can go buy it. It's consumer level product now. That's the change that's happened over time. So I just grabbed these pictures off of the web. And so here's no ray tracing of some scene. So here's path tracing. You can think of this as ray tracing with one sample per pixel is what this means. And you see it's quite noisy. We were talking about the noise. If I only do one sample per pixel, we have a lot of noise. I'm not sure if this comes through the Zoom, but there's a lot of salt and pepper pixel noise here. If I do 15 seconds of adding everything up, you can think of this as ground truth, right? If I had plenty of render time for this one frame and I sent enough samples for 15 seconds, I get a really nice picture. This is everything. So here's a comparison to a hybrid ray tracing. And I don't know exactly what they mean by this, but I think what they mean is we start with the raw ray tracing output, this super noisy thing, and then we do some kind of magic machine learning or image processing or something else to combine this picture with remember we had a no ray tracing picture. So this is what you've all been rendering so far. The graphics card can definitely do this fast. We have the no ray tracing. We now have the raw ray tracing output, and we somehow have to combine those things to get this hybrid picture out. Now, exactly how we're doing that combination, I don't know. So what's actually happening in the modern ray tracing to get it to be real time appears to me to be more complicated than do what we said in this lecture and then just send more rays, right? Do what we said in this lecture and send more rays is this 15-second accumulation. It doesn't get us to real time. So I think to get to real time, they're essentially sending only one or two rays per pixel, because we don't have a large budget to be sending thousands of rays per pixel, which gets us to this terrible picture, right, that we wouldn't want to use directly. And then we somehow have some smart merge. So I think the fact that modern graphics cards have a little bit of learning, a little bit of image processing, a little bit of 3D graphics like we've been doing, now have the ray tracing, you put all that together and you can finally get sort of this hybrid picture out of them and get these effects. So it's taken quite a bit to get there. Am I over time? Soon. Thank you for putting that in chat.